Bueno, algunos de ustedes expresaron un poco de preocupación por el tema de comprensión en inglés. Yo lo que creo es que puedo empezar en inglés y cuando lleguemos a temas un poco técnicos o más complicados, yo puedo cambiar por español o hacer una traducción, porque algo que suele pasar es que uno al inicio empieza suave o bien y luego se les pasa un concepto por el inglés y luego uno dice, pero es que me da pena preguntar, ¿sí? Entonces igual lo voy a hacer en ambos idiomas. Yo sé que hay muchos que quieren practicar el inglés y por eso les gustan estos cursos que son ofrecidos en inglés, pero tenemos que hacer un poco de ambos para que no todos, para que no hay nadie que no entienda algo, ¿listo? Entonces, pues, empecemos de esa forma. Voy a empezar con pantalla. Ok. Sí. Okay. I'm going to start with a question. You guys can answer in English or in Spanish. You can answer in the chat or with your microphones. But I wanted to ask, whoops, before we start, what do you think the Earth would be like if plate tectonics didn't exist? So let's shut down mantle convection and moving plates and moving continents. What are some of the consequences? What do you expect? I can open a whiteboard here, maybe better. Or is it too early in the morning to think? Okay. There would be no mountains. That's true. What would happen to any mountain that had been built in any moment? Interesting. Okay. So Ana Maria, you say climate, and Karen, you say very big volcanoes. So let's start with the climate one. What would be different about the climate without plate tectonics? How does plate tectonics? Oh, I have my drawings from yesterday. Looks strange. Okay, the Earth would be colder. Oh, these are very interesting ideas, and actually, some of them I've never heard from students before, so this is interesting. Okay, so continents, as we know them, may not exist. Okay. Interesting. Any other ideas? What might be different? These are all excellent.
With regards to climate, without tectonics, I think it might happen something like with Venus.
Okay.
Like there would be a concentration of volcanic eruptions in a certain amount of time.
Okay.
They will all explode at the same time, and some very huge gas clouds would form.
Okay, interesting. So instead of having moving plates and maybe changing volcanic hotspots, you're saying it would be in one place. Maybe. Okay, why would there be volcanoes?
No, it would be like rather a bunch of hotspots that erupt all at the same time. I think that's what
Okay.
happens in Venus, that all the pressure accumulates in the entire planet, and at the same time it explodes.
Okay, interesting. I don't know if you guys have ever made maybe like a very thick soup. I don't know. Do you guys ever cook? But if you've ever, I mean, if you boil water or you make something like chocolate, it's liquid, so you know it just starts to boil. But I don't know if you've ever tried to reheat very dense soup in a pot, and have you noticed what happens? You're gonna have to try these cooking experiments to do geodynamics. They can be your analog models, right? So if I have something very viscous sitting in a pot of water, I mean, on a stove, right? And I heat from the bottom, in time, if I mix my soup, it becomes runny, right? Like if I take the soup out of the fridge and it's very thick and then I put it on the stove, if I just leave it very hot on the stove, what will happen? Besides it burns, because it also burns. Have you guys ever had experiences like this in the kitchen, or am I sounding crazy here? It's very different from boiling water, and it's different from even boiling milk, right? Although interesting things happen when you boil milk. What actually happens when you boil milk? You've all made hot chocolate, right?
It becomes more liquid.
Okay. So it becomes less viscous because I heat it. This is also true of rocks. And if I stir my soup, it'll eventually start to convect, right? So if you guys make hot chocolate before it boils, you'll see like these rising like cells of convection. Usually you end up with natas, right? So that's a good approximation of maybe what happens on the continents if you had a very liquid mantle. But if I have my very thick soup, I don't know if you've ever had the experience, but if I don't stir it and it's very dense, it actually first kind of lifts up and goes. These are things I maybe notice too much, but you get these bubbles at the top, and because it's so viscous, it's very hard to make it move and convect, but you still have to let that hot air out, so it comes up and kind of lifts up the whole thing, goes, and I end up with bubbles at the top that always burst at the same spot. So this, I think, would be one way of explaining what happens on Venus, where, of course, the interior of the planet is also hotter, but instead of getting convection, I'm kind of blasting hot stuff straight up. And so I'm going to keep building these volcanoes. And as Karen says, they get big because it's in the same spot. So I can end up with those mega volcanoes. Anybody who's interested in doing their project on, for example, Venus, can try this experiment with two liquids and see what happens when I just have something that's dense so that it won't convect, but then I still need to move a liquid up from below that's light to see what I can get instead of convection, because this is one of the theories of what happens on Venus. Okay, so these are all good ideas. No mountains. Remember, we always have this fight between building a mountain and eroding it off. If I turned off plate tectonics right now, I would get rid of the mountains. They would erode away. Has any of you ever thought what would happen? Would we have one thin continent and no water, or would we have everybody underwater? And how would you know? Todos entendieron eso, sí. Como la pregunta es que sin placas tectónicas no tendríamos montañas y tampoco tendríamos los continentes como los conocemos. Pero ¿qué pasaría? Porque igual hay material más livianita que se diferenció durante la formación de la Tierra y está en la superficie, la corteza, ¿sí? Pero ¿qué pasaría sin esa dinámica de empujar y separar continentes? ¿Tendríamos algo como Waterworld, todo cubierto con agua? ¿O tendríamos como todo apenas saliendo? ¿O qué tendríamos? What do you guys think? Laura, Atlantis. Why you say Atlantis? These are all relatives. Waterworld sounds nice. Did you guys, I mean, you're too young to have seen this movie. If there any other reason, then you'd like weird old movies. But there was this movie, I think it was in the 90s, called Waterworld with Kevin Costner, where I guess it was climate change and the sea level lifted and everybody had to live on water. Anyway, it was a really bad movie. But what was interesting about it is the question people had of, well, why would it be covered with water? You can't make sea level come up forever. But yes, so Laura, the continents would eventually be completely eroded. In theory, they should kind of all spread out, right? And sediments would fill the oceans. So do you think we really would have Waterworld, or would we still have like islands, or what do you think? That's another thing. Yes, Juan Pablo? Juan Pablo, you have your hand up? I can't hear you. Or is there an accidental hand? Okay, ya te escuchamos.
No, quería levantar.
Okay.
The trenches will disappear.
Okay.
Mariana Trenches? How do you say it in English?
Yep. The ocean trenches, the subduction trenches, yes.
No, but specifically Mariana Trench.
The Mariana trenches, yes.
Está bien, esa desaparecería. Bueno, todas.
Okay. Yes. So all of these things you guys mentioned are true. It's a backwards way of saying that all of the things we do see are evidence of plate tectonics. And what we're doing right now is kind of a version of thought experiments to come up with a conceptual model, right? What would happen if, and when you think of a theory or a hypothesis, you always have to say these what ifs, right? What if this were true? What should I see? And that's a prediction. And then you can build on more and more evidence, right? So I can say, well, I predict that, I don't know, there would be no mountains, or there would be this or the other thing. And we can't do this experiment on Earth, but we can look at other planets, as you say. So the big volcanoes sounds like a nice idea, but we can actually go and look at Venus and say, okay, that is what happens when we have a planet that's a bit different than Earth. So one consequence of not having tectonics would be that, okay? All right, so it's actually difficult to think about. You guys have all learned tectonics and we all have it into our heads, so it's hard to imagine something else. But you've done a good job of imagining a world without tectonics. What if I were to ask you to come up with a completely different explanation for all of these observations, like continents and mountains? We're a little bit contaminated by knowing the theory, so this would be challenging, but it's one possible project idea. Okay, so the way people arrived at plate tectonics was very, very slow and with many bumps because it's not something that was obvious. It's not something that was intuitive to think about. Wegener's idea was completely crazy, of course. And then the evidence kept mounting. So eventually I had to explain it. And what happens usually in a theory is you don't get the whole story. You get, well, the continents move. We'll start there, right? So if we start with what's really the difference between plate tectonic theory and continental drift, what do you think the main differences are? Juan Pablo?
Sí, esta yo me la sé. Pero bueno, que esta sí me la sé, esta pregunta. La respuesta a esta pregunta.
Sí, entonces, ¿cuál es la respuesta?
Pues que no puede ser verdad. El movimiento de los continentes de Wegener solamente es una observación a la teoría de la tectónica de placas, y que en realidad la tectónica de placas es una unificación de muchísimas observaciones geológicas, como por ejemplo que es paradójico que los lugares más profundos de los océanos estén más cerca a los continentes que en la mitad del mar. Eso no tiene mucho sentido, pero apenas uno tiene en cuenta la subducción se da cuenta que eso tiene sentido, y eso es de tectónica de placas. Entonces lo que quería decir es que la deriva continental es solamente una observación de las muchas que unifica y explica la tectónica de placas. Entonces básicamente sería como algo más pequeño, es lo que quería decir. Y que,
muy buena respuesta.
Sí,
dime
pero
más.
falta algo, que la tectónica de placas en geología es como la evolución en biología. Es una teoría unificadora que unifica nuestras observaciones y no les quita validez. Entonces es un hallazgo muy importante en las geociencias. Y eso ya es todo.
Ok, excelente. ¿Están todos de acuerdo? Bueno, excelente respuesta. Yo creo que lo describe básicamente todo. Y muy bien expresado. Hay un tema que es interesante, que es digamos, esa es la teoría más fundamental, es como dices, que la teoría de la evolución en biología, que explica tantas cosas que ya muchos misterios de una se contestan. Lo que es interesante, y yo creo que también en paralelo con la evolución, es que hay muchísimas más preguntas ahora por tener esa teoría pues nueva, que son para investigación. Y yo creo que es algo que si les interesa el tema de tectónica, no es que es algo que se ya solucionó, es algo que generó tantos problemas interesantes individuales en diferentes partes de la Tierra, que todavía, a pesar de tener esa teoría tan completa, no se puede explicar por completo. ¿Sí? Algo, bueno, algo que, por ejemplo, es todavía un tema de investigación, que de pronto ustedes ya hablaron en sismología, entendemos muy bien el tema de sismos y cómo se generan y por qué están asociados a bordes de placa y qué tipos de fallas los producen, pero algo que todavía está en debate son las causas de terremotos grandes dentro de la placa, lejos de un borde de placa. Y hay diferentes mecanismos dinámicos que uno puede debatir. Entonces, lo interesante es, teniendo esa teoría, se puede hasta generar más problemas y observaciones interesantes que de pronto a nadie se le ocurriría antes. ¿Sí? Y eso, para que entiendan que el tema de tectónica y geodinámica es una área activa, viva, nueva, emocionante para estudiar. Y ojalá en ese curso vean muchas cosas que les como fascinen un poco el interés para estudiar, ¿listo? Entonces, muchas gracias, Juan Pablo. Gracias a todos por sus buenas ideas. Yo creo que pues lo que tenía pensado en esa clase es desarrollar un poco la parte histórica. No sé qué tanto ustedes conocen la historia. Por ejemplo, mencionas que es una observación, la deriva, y eso yo voy a compartir pantalla. Oh, antes de empezar eso, remember I gave you a little Turupe problem? Did anybody think about it? About whether gravity should make the ocean go down because of a topographic high or up? Anybody think about that, or have you not thought about it yet? Because if you didn't, I'll get you to think about it more. And then when we get to talking about how gravity is related to information about geodynamics, we can talk about the bumps on the ocean. So let's save this discussion maybe till the end of the class or for next class, but think about it. So remember what we had. We had, can't make this thing draw. We had a mid-ocean ridge, maybe. Let's ignore what's happening below the surface. Just say we have a bump, a mountain on the bottom. And this is the surface of the water. Do you expect the water to do this, or stay flat? So that was the question, right? We'll come back to this again when we start talking about gravity and isostasy and how the shape of the Earth is related to its dynamics. But that's just to start with thinking intuitively about gravity and what it may tell us about the Earth. Okay, let's see. I lost my chat. Okay. Okay, good, Kristen. You stand with the affirmation that the water goes down. Anybody has a different opinion? Okay. Think about it a little bit more. You have a puente. You can sit there and think about mountains on the ocean floor for all weekend. Maybe it won't change the level. That's also possible. Why do you say that? That's an interesting thing to say. Interested to know maybe what provokes that idea, or is it just kind of an intuitive idea?
Sorry, I say the water goes down because that I mean we can think. For example, at first that there is no mountain there. The gravity is homogeneous. So we have a certain sea level, but if we add that extra body that adds some gravity,
Okay.
we can think that there is an extra force of gravity that pulls
Okay.
the water down.
Okay. So it's like almost like the opposite of a tide, right? Like if I think about the Earth and the moon, and I say the moon pulls hard on this side, so it lifts the water here. It's kind of a little bit of an analogy with saying, okay, if I have a mountain here, I should pull the water towards it, right?
Exactly, that would be my thought.
Okay. That's a very interesting thought, and I think probably there's many people who are saying nothing who would agree with you in this class. Does anybody have another way of looking at it? Okay, so Sergio, you're saying that the water is liquid and it should be in equilibrium. All water increases the level, but okay, so the idea then is to say, because it's a liquid, it should be flat, and so instead of bending, it should just move either higher or lower. Okay. This is great. We have two completely different ideas that both make sense. This is what I like in geodynamics. And this is what happens in conferences when people begin to fight about why there's melt in different parts of the crust, or why the lithosphere changes its angle. So it's fun. Does anybody have a way to resolve these two completely different ideas that both seem pretty realistic?
Measuring.
Okay, so this is a fantastic idea. We have to do the experiment. We have to go and measure sea surface heights. So if you guys want, there should be sea surface height data available online, maybe actually even published papers that show this, but observations of sea surface height are, of course, as I mentioned last time, one way of figuring out what's going on underneath the geodynamics. So go and look at it. Find sea surface height data and then tell me about it next week. Because this debate, I want you guys to figure out.
I would have a counter argument for Sergio's statement.
Okay.
That would be that this body, this rock mass that we have here, is not pulling with the same strength all the water particles. It pulls stronger the ones that are closer, of course. So the water particles that are closer would feel a greater force, and thus they will come down even harder than all the others that are further away.
Okay, so you're saying it really will pull harder here than over here, so the water should come down.
Yeah, it should come down like more with the water that is closer, and less with the water that is further away.
Okay, so let's try to draw something like a little force diagram on the water particles, and you're saying something like this. Like, okay, so this mountain should attract, but it might attract a lot here. So this particle will feel it. This one maybe less, and this one even less, right? So then you say, oh, okay, so it should pull down here. Yes?
Yeah, exactly.
Okay. What if I took it to an extreme? What if this was made out of, I don't know, what's the heaviest element you can think of compacted in here? Should the water then disappear here? You can take it to an extreme. One way of trying to figure out if something that we feel intuitively could be true is to take it to one extreme or the other, right? So one extreme is get rid of the mountain. What happens to the water? Okay, we say it's flat. What if I made the mountain really, really, really dense or really, really, really big? Would the water come down and bear, like would I end up with maybe the mountain sticking out of the water like this?
I think it would compress around the mountain.
Compress around the mountain. So can you guys draw? Will it let you draw? Can you draw what you mean?
I don't know how to
Does it-
draw that, but
Okay, you don't. Does it let you use the little pencils?
Yeah, but there are
Okay.
so many lines already.
Oh, let me erase it. Okay, so you have a fresh board to play with. What do you think?
Okay. So I have no.
Does it let you? Do I have to give him permission or something?
You can see
I
my
have
drawing?
it.
Okay.
Yes. Okay.
So we'll do some. I think it would do something like this.
Is that the mountain or the water?
The blue one is the water.
Ah, okay. Oh, interesting.
So let me explain.
Mhm.
So the force of the mountain, the gravitational force of the mountain, would be pulling the water down. But
Okay.
once there is too much water here near the mountain, the electromagnetic force would act like a spring between the water particles. So here in this part, the water would be a lot denser because there would be the
It'll compress.
gravitational force would be squeezing it, would be compressing it.
Okay.
So it would not just go down here, but here there would be an equilibrium between the gravitational force and the electromagnetic force that is pulling the water upwards. But here, where the water is not so much compressed, the gravitational force would win, would take it down.
Okay.
So
Interesting.
it would, I think it would have this shape, the water, if the mountain was really dense.
Okay. Very interesting, Christian. Does anybody have any questions or comments for what Christian said? This is very interesting. Okay. Let's see. Laura or Karen, you only ever write in the chat, but you can answer in chat. What do you guys think? Okay, well, there's a question. Can water be compressed or squeezed? That's actually a good question. What property of material would tell me that? Water cannot be compressed. Okay, Laura.
Because it's Newtonian, a Newtonian liquid.
Okay. So it makes it hard to squish, right? Do you guys remember in Mecánica Continua when we talked about properties such as, I don't know if you did bulk modulus and compressibility of materials? Or is it too long ago that you took the class? Or is it the language? What do you say? How do you say bulk modulus? Modulo de compresibilidad, I could say. I don't know how it was talked about. Did you remember doing those topics?
Sí, sí.
Okay. So the question is, can I squeeze water the way that Christian was suggesting in his model?
No, pues a priori no, porque los
Okay.
líquidos son incompresibles.
Okay. So Christian, would your model need water to be compressible, or can this happen without water compressing?
Okay, so the problem with that, I think, would be that that would be roughly an idealization. Let me draw something here. There would be some pressure coming from here.
Okay.
And some pressure coming from here. The water generally cannot be compressed because it deforms. It changes the shape in response to the stress that one is put in it. So there is this force that is kind of stopping it from this part of the water deforming in this direction. and this other that is stopping it from deforming it in this direction. So in the end, what I'm trying to say is that there will be an equilibrium of forces here between the pressure that the water is exerting in this direction and in this direction, and the pressure that the water of the rest of the ocean would exert in this direction and in this direction. And here there will be equilibrium of forces between the gravity here and the water trying to not be compressed.
Okay.
But in the end, there will be an equilibrium here of forces in all directions.
Okay. Well, thank you very much, Christian. This is really interesting. And actually what you developed was quite a full model. This is impressive. I'm hoping in this course I can get everybody to start thinking of conceptual models for different things. And actually for your project, this is the kind of thing I want you to do. I'll give you a list of topics. And what I want is and you can do this in groups. Anybody who really, really hates working in groups, please talk to me. You can do it by yourself if you really want to. But one of the things that's important, as you see in the class, is that if somebody proposes something, having somebody throw out an idea like what Laura says, water can't be compressed. Okay, so I have to rethink that part. If you have no interaction with your friends, it's harder to do this really well, okay? In the scientific community, it works like that. There's not very many papers with one author, and you think, well, why? Usually somebody has not only ideas and counter arguments that make the thing better, but it's also other people are experts in other types of evidence. So you might say, okay, look, I've already taken seismica and you guys haven't, so I'm going to propose that you include this, right? And real science really works that way. So in your project, what I want is for you guys, you're going to have to make a model, but it can be something conceptual like this. The only thing I'm going to ask you to do is support your model with some kind of evidence. So in this case, it would be bringing in observations of the surface of the ocean, or it would be making your force diagram and arguing based on physics what should happen and then arguing it with the math. Or you can even do a numerical simulation for those of you who like doing computer modeling. And the idea is to argue for your model. So this is a very preliminary little example of what kind of thing you can do. And then I want you guys to start thinking about this for your project. So think about two things. One of them is, who do you want to work with? Okay. It can be up to 4 people. More than that, and it just becomes, it actually slows down the work, I think. There's a law about papers with too many co-authors that once you have more than 4 or 5, it can make many, many more months before the thing gets approved because everybody wants to argue about what to put in it. So let's say maybe 4 people, and build a little model. So I will give you some topic ideas, but this is one example of a topic. Okay, so it's a simple idea. What should happen to the seafloor if I do this? I mean the sea surface if I do this. If you think of your own idea of what you want to model, I'm happy to do it. It can be a real problem in geodynamics. Obviously, it has to be simple. This is just a course where that's one part, so you don't have to make a super model or anything. But the idea is to make a little model, okay? Okay, so let's go back to plate tectonics. This topic will come up again in gravity because what I find interesting about gravity is that in spite of all of our tuition and all of our experiences that we have with it, we always think we know, okay, well, this is going to fall like that, or this should do this. It's actually has some very non-intuitive parts, okay? And things like this are included. That's why I like this problem, okay? So in the course, I'd like you to develop this intuition a little bit, but we'll have to sometimes do math that disproves our intuition, right? And actually, even if you look at the history of the theory of gravity by Newton, a lot of what comes out of that is very not intuitive. No, Aristotle thought that different objects should fall with different velocities, for example, depending on their weight. Newton shows this is not true, but it's something that everybody feels, right? So these things, sometimes science is actually a fight with our intuition. Okay. All right. So let's look at this. Try to share this. Okay. So we've done this part. What you were saying, I think now I can't even remember, was it you, Juan Paulo, who explained this idea between a continental drift and tectonics? You mentioned that continental drift is an observation. It's a little bit removed from an observation because it's based on some simple observations that everyone could make. It was not especially scientific. I mean, you could see the shape of the continents in a map. And actually those continental shapes, it was not the first time they noticed them. There was actually, in the 16th century, there was a map maker who made this for fun, this little drawing, because the rompecabezas is a little bit obvious, right? So the jump that Wegener made was to say that it really was like that and it moved. That's the part that's now a theory or a hypothesis in his case, right? Okay. This generated, of course, a big noise in the scientific world, because this is kind of offensive to people who have been studying the Earth and how it works and had an idea already. You'll find this with sciences that the egos sometimes get in the way. So often a new idea, it doesn't matter how well supported it is, people will resist. This is not what we were taught in school. This is not what my professor told me 5 years ago. Probably things we'll talk about in this course. In 5 years, you'll say, but they already, got rid of that part and now they know that, for example, dynamic topography does not work like that. So keep in mind, not everything you learn will be true. What you learn is what people understand currently about the state of the world, okay? So when somebody comes along and says, you're all wrong and the Earth is completely different than what we thought, people don't like it. So that's the first problem. So this map maker did not even suggest that it moved, but it was this crazy guy who decided the continents moved, because not only this map, but the fossils. Okay, so he was an observant person. He looked at this, not just the rompecabezas, but the fossils. He says, we should not have tropical fossils in Antarctica. This is crazy. So the only way that could have happened is if Antarctica was somewhere else before. Now, this is very logical. But as I say, this is also something that everybody began to jump on him and say, come on, this can't happen. You might as well tell me that the continents went to the moon and back. So this is difficult to swallow. And actually, I know people who didn't believe really plate tectonics, even when they were young students in the 70s or 80s. So some of my mentors and professors were resistant to plate tectonics when they were young, which is kind of a crazy thing to think about. But what really were the ways that people attacked this? And they had reason to attack it, because the first question, of course, was how? So that's the part where you say it's not a complete theory because we don't have the how. And I can look at all the observations I want, and I can say I can count all the fossils, but I still don't know what's pushing those continents around. Okay, so first, they didn't know what force would do this, and this is fair enough. They had no idea what was inside the Earth. But it's more, if you even think of, let's say you had some kind of amazing force that we can't think of right now, but that could move them. They predicted that there should be other observations. For example, if I have a tooth in my jaw, let's think about it like teeth in my jaw. Does anybody here have brackets? You know how that feels when they tighten them, right? If you've ever had brackets, they put them on your teeth, and then when they tighten them, you kind of feel bad all day, like, right? So this is your tooth moving inside your jaw. It hurts, okay? So I think when Wegener says the continents were moved around, in those days, this was more than 100 years ago, what we saw were the continents. The water was the water. Nobody had any idea really what the deep ocean looked like. So what people thought was, well, the continents are like teeth in a big jaw. So here's the Earth, and the continents like here and here and here, and I have water filling in. So if I want to move that, it would be like moving teeth. So if something's pushing those continents around, it's like putting brackets on your teeth, but trying to do it fast. I should actually like pull a big hole in my jaw, right? this is, you would need a very, very big force to do that, second of all. And then what I really should do is have big cat scratch marks all over the bottom of the ocean where the continents were pulled around like teeth. So people said, this, you know, nothing will push those continents around. And besides, I should have these big holes in the bottom of this floor, ocean floor. So I think the fight there died because the only way people could think of moving continents is moving them around inside solid rock like teeth, because they didn't know what was below. So this is the part where we need more layers of explanation. Okay. So if we saw, as we saw with our little Turupe example, you guys already proposed what observation we could make to resolve this conflict between whether I should get a bump or whether I should get a hole. So part of the thing is, okay, we don't believe it's moving around like teeth. Nobody believes that. But then how do I explain those fossils? We're back to the same, right? Like, we know there's something to explain. So people did begin to explore other ways of looking at the Earth. And this is it gets more interesting, because this Wegener's first talk was in 1912, and it was in 1928 and 1935 that people began to create what you might call a model. Okay, so pushing the continents was an idea, but the model has to have the mechanism in it. So Holmes said, well, maybe the Earth convects. Now this is fascinating because there was no reason to think so. He had no evidence for this, but it was an idea. And I guess, you know, if you look at your soup pot and you can think like this, you can think the Earth maybe is like your pot of soup, and that there has to be a heat source and it moves around. Okay. Now the idea that Holmes had was that it's radioactive heat making this heat-driven motion. Radioactivity in those days, remember, was a new idea. It was the turn of the century that they even knew that radioactivity existed. So this was quite a hot topic, no pun intended. Okay. And then the mathematicians jumped in, and physicists, and began to say, okay, well, look, if we do that, we can generate convection at this speed, and you know, depending on the property of the rock, we can make the whole world convect at about 1 centimeter a year. So Pecoris was our first mantle dynamic modeler without knowing anything about the mantle, and even that there was really a mantle. So these are really, really amazing ideas, right? So these people clearly were looking for a way to move the teeth around the jaw, because they did believe that Wegener's idea was good. There were still people who said, no way, nope, continents did not move. But the people that kind of were bothered by this fossil thing, and they said, we really think there's something to explain, went ahead and made models. Okay. And then the evidence began to pile up. So you guys know also about the glacial evidence. So all of the southern parts of various continents that touch the southern hemisphere are covered with glacial stria, and evidence of glacial erosion features. And they said, okay, so again, just like the tropical animals in Antarctica, we can't believe that there's glacial stria in India, so it has to have moved. And then this rompecabezas came later. Okay, so this was additional evidence to what Wegener had. Wegener didn't have this, but it gives an extra piece. Not only did the continents fit nicely, but look at how, if I put a glacier on it, it explains all that glacial erosion. Okay, this is getting more and more difficult to fight with. But at the same time, in other areas of geology, people were doing other things. So you guys remember, if you can explain the paleomagnetic evidence that helped support plate tectonics? Who would like to describe it? Juan Pablo.
Well, when the rocks are formed, the rocks, the basaltic rocks that have some ferromagnetic minerals elements.
Okay.
And they are susceptible to the magnetic field, so they aligned some particles, and these particles in some terrains, are aligned inversely to the nowadays magnetic field. So
Okay.
that magnetic field had to move or inverted, but I don't know how to use it use that in order to help Wegener.
Okay, excellent. Thank you, Juan Pablo. This is correct. And the reason why it helped Wegener is a little bit more complicated. Does anybody remember why this helped Wegener? You don't have to remember a specific location or anything, but just like in general, why would being able to observe magnetic fields help you? Laura?
There is a point at which, when the basaltic rock cools, these minerals, like, well, they're aligned according to the magnetic field, but there is a temperature at which, like, they cannot move any longer.
Okay.
Because the rock cools down. So then, as they are displaced, you see that they don't really, they're not aligned like to the magnetic field today, but you could assume that it was aligned to the magnetic field at the time. So that kind of shows that it has moved.
Okay, excellent. Everybody understood both Juan Pablo and Laura's points? You guys understand each other when you speak English better than you understand me, right? Maybe.
Prende el micrófono.
Okay, about the same? It's interesting because I'll give you an example. I always found when I first came to Colombia and I didn't speak Spanish and I started to learn, I understood Leslie better than anybody else. And before you think this is weird, people who speak the same language make the same mistakes. People who speak it as a second language talk slower. And the accent is more compatible with what our brain is used to, and so we can interpret more what our friend is saying in another language, because their accent will be the same. So if you guys had to listen to somebody speaking English with a very different accent, I don't know, like, well, how about JB? JB has a French accent. Does that sound harder to understand or easier to understand than
No,
mine?
ese es como 60 veces más difícil.
Okay. Y es porque su primer idioma es otro. Entonces JB tiene, sí, JB tiene muy buen español, pero tiene un acento tan diferente que el mío, que cuando habla inglés no suena como hablo yo, ¿cierto? Okay. So that's the idea, basically. We have these trapped magnetic fields that then tell you something about the past. In this course, I want to do a little bit of paleomagnetism. I want to start by saying I'm not a paleomagnetist. We're not going to go into the physics of the magnetism or anything because it's not what I know. But one thing that's very interesting is being able to do tectonic reconstructions with paleomagnetic data. Okay, and this is relevant for understanding where the plates were. Did you guys ever do a little bit of this in maybe tectonics or any other course? Talk about paleomagnetism? For me, paleomagnetism is fascinating. I took one course where we learned about it and I thought it was really cool. But what's really cool for me about it is what it can do. So Christian, where did you learn about paleomagnetism?
No, in general commentaries of many geoscience courses. Sometimes geomagnetism comes up, but we don't necessarily go too deep into it.
Okay, so with Bogdan, so the applied side of what you can do with magnetic field data and remnant magnetization, I guess, right? Magnetic susceptibility and geophysical studies, maybe a little bit.
If I can recall, talking about the continental drift, he said that in the whole continent, the magnetite crystals in fresh volcanic rocks points to the current magnetic north pole, but there was evidence that there were rocks in different continents that pointed to the same place, but that's not the actual or the nowadays north pole. Then we can assume that in some point in the history, they were pointing out the same place. Then maybe it moved. They moved.
Okay. Excellent. So now we have the final piece of the puzzle. So thank you, Juan Pablo, Laura, and Santiago, because now you understand the magical thing that paleomagnetism could do to convince people that continents moved. So I want to, okay, let's go to this slide because it's, here's the idea, right? One thing, it's very hard to observe the ocean floor because they hadn't explored it yet, but the Deccan Traps in India, you guys have learned a little bit about this, where there were repeated eruptions of basalt forming a very, very thick layer in India called the Deccan Traps. This passed over a long, long period of time, so there was enough basalt there to actually see changes in the magnetic field direction, okay, because it was moving around. Now, it's not the only interpretation. If I look at rocks in different continents, I can say, all right, maybe the pole is moving around. Like, let's say in India, in the case of India, I'm not sure if this is, I can't even see India here. Okay, I can find the magnetic pole today, and I see the most recent rocks align with it. But if I go back 10 million years, I see that the apparent direction of north had moved. And then I go back another 10 million years and the north was somewhere else. I can draw what's called an apparent polar wander path, okay? And I can say the North Pole moved like this. Dunk, 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 dunk. Well, one argument is, okay, so the pole moved and India stayed there. So what do I have to do? I have to measure different continents that maybe move a different way. And that's what they did. So let's see. Here. If I look at only one continent, I can say the pole does this, okay? Or my alternative is the pole stays here and the continent did that. The only way to resolve that is to look at different continents, and that's actually what they did. So what they said is, okay, according to India, the pole did this. Duk, 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 duk. According to North America, the pole did this. Duk, 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 duk. And so unless we're convinced that there's a different magnetic pole in different parts of the world at different times, we know that the continents had to have moved. So this was the first evidence. It was not an explanatory model, but it was an evidence that really it had to have moved, okay? So the fossils were an idea that I had to have these two continents stuck together in order for the fossils patterns to make sense. But people happily proposed other things like the land bridges and other stuff. So they said, it's not the only explanation, but how are you gonna fight with this? Okay, we know how the magnetic dipole looks. We can imagine that it moved, but we can't imagine that it moved in a different place for every different continent. So this was pretty much a smoking gun that we know the continents moved. Once you know that, it really is just now a debate about how again, but we're now convinced it's true. So this was really key, okay? It got more interesting when they were able to observe seafloors, because then we can actually see the creation of new crust, and that's a different part. That's when we start talking about tectonics, okay? So apparent polar wander is an interesting way to do constructions of the movements of the plate, and we'll do a little bit of that, okay? I can give you guys magnetic data from one continent over time, and you guys will be able to construct how the plate moved. This is something, it's just math, it's basic geometry. It's easy to get confused with, even though it's basic geometry, so we'll do some exercises later in the course, but it's kind of fun, okay? So this is the idea. You take all these different pole paths and you can make the continents move in a way that it's consistent and figure out the earlier configuration of continents. Any questions? Are we being reminded of things we already knew, right? A little bit. Okay. So are you guys familiar with Euler poles? Did you do this maybe in tectonics?
Sí, yo lo vi en estructural, pero eso es para describir cómo se mueve una parte del área en una esfera a partir de un vector, bueno, no sé, pero no soy bueno.
Okay. So let's say if I have a map with different tectonic plates, will you guys be able to find the pole of rotation between those two plates? Maybe using mapping methods?
No.
No? Okay, you didn't get that far. in this course, we're going to do a little bit of that. It's easier to do with math than maps, or at least I think so. But the idea is if you look at any part of the motion of a continent, you can calculate its pole of rotation, right? So just like the Earth has an axis of rotation where it goes like this, the continents don't obviously move on a flat surface, they're moving around. And if they're moving around, it means they're rotating around an axis, okay? So not our Earth's axis, but maybe its own axis. And we call that an Euler pole. Now this, you can actually use the patterns of seafloor ridges and faults on a map to actually calculate it graphically. But we can do it actually even just with cross products. It's cool. So we'll start talking about that, about what it means to move continents around on a sphere mathematically. So we'll do a little bit of spherical geometry, which I'm not sure you guys have ever done. Okay, so that's another tool, is that when you're doing mathematical problems on the Earth or geometrical problems, you're usually using spherical geometry, right? So if I have a big sphere, I don't have triangles that look like this. I have triangles that have less or greater than 180 degrees inside because they're on a bloated surface or a sunken surface. So it's kind of fun. Did you guys ever do any spherical geometry in a math course or anything?
Uy, no, gracias a Dios, no.
Gracias a Dios, no. Oh no, it's fun, I promise. Well, geometry is interesting, but spherical geometry has some quite fun parts, and I really promise it's not hard. If you guys did geometry in high school, this is just geometry with slightly warped laws. So you still have a cosine law, a sine law. You can still sum the interior angles. You can do these things, but it's on a sphere, and we have to do it on a sphere, more or less. At least I don't make you do it on an ellipse. We'll do it on a sphere. But it allows you to do things like calculate Euler poles and paths of continents, and using just paleomagnetic data. Okay, so without spherical geometry, you can't use that paleomagnetic data. So we'll do a little bit of spherical geometry, but it's more or less high school level. It's what you did in high school, but on a sphere. Okay, so that's we'll get into a little bit of the mechanics of how this all works. One thing that's interesting is when we get to the plate tectonic theory, is we always talk about just the plates moving around and some of the interesting things that happens at borders. But a lot of tectonics is really vertical. And when you think about mountain building, that's obvious, but there's many different things that if I stop just thinking about a dimensionless rigid plate and really begin thinking about a slab with properties and lengths and differing densities, interesting things happen inside the plate. Okay, so we will get to that. And these are the parts of tectonics that are still actively being debated. Okay, so this paleomag thing really won Wegener his argument, even though I think he had already died by that point. And then the big fight was for the details, right? So if you look at the parallel with physics, which had a similar history, modern physics, you know, in Newton thought he had it all figured out, and everybody said, okay, physics is dead. There's no more physics. We know everything, which is always funny. And then Einstein came along and said, you're all wrong, and came up with his gravitational theory that was different than Newton's. But what's interesting is it passed through sort of a similar thing. Nobody believes you. Okay, and then prove it. Einstein did prove it with observations, astronomical observations. But today, there are still physicists painfully plugging away at Einstein's equations, trying to figure out the details. So it's similar to plate tectonics in this way. We kind of have the idea, but now we have all these mysteries to solve using that theory. Okay, so I promise that geosciences is also not dead. What happens, and this is still happening today, is that as our technology gets more sophisticated, we have more possibility of proving people wrong, and scientists love to prove everybody wrong. If you go to conferences, you know, even people who are friends will be at each other's throat in a conference talk. And it's because it's more fun to prove someone wrong with a piece of evidence. It's actually easier to do than proving yourself right, right? This concept of falsifiability in science is important because otherwise I can invent whatever I want and say the plates are being carried around by turtles. But if somebody can come up with a piece of evidence that proves me wrong, then actually my theory is scientific. So people happily run around looking for evidence to prove each other wrong. It's a quick way to get a paper. It's a quick way to go, ha ha. And people do it all the time. Now, this is good for science because it means nobody can get away with a bad theory for very long. So let's look at the types of observations that began to happen, right? Seismology is also new. So in the 1940s and 50s, they began to sort of study seismic activity and do some seafloor observations. They actually used to send stuff down there. You can do sonar, you can do things to measure the depth, right? And there were some interesting things. So first of all, they never found the big holes in where the teeth moved, so that's good. But they found something unexpected. I think what they expected was that if you have continents like this, then the ocean should be like a bathtub, right? Maybe getting deeper in the middle, shallower on the sides, right? Again, like our teeth. Okay, so we have gums down here and then another tooth and then gums and tooth. What they found was very, very surprising. Of course, you guys know this story. These mid-ocean ridge trenches were a complete wow. Because even though we really believe the continents moved because of magnetism, and even though, okay, now there's more evidence, and some people made some models, this ocean trench and ridge thing was very weird, and this was not accounted for. So as Juan Pablo said, this required a more complete, proper theory that could explain all of that stuff, the paleomagnefossils, these weird explanations here. And the person who did a really cool model, in this case, was Harry Hess. I found the paper, so I can put it on Looking Known. But this was a complete, like, what's that? Now, because plate tectonics was not known, but the continental drift was now believed, the idea was just to put that into our continental drift idea and see how it fit. So it was not so, if we'd seen this and we didn't know continents move, nobody would have known what to do with that, okay, this ridge thing. But Harry Hess says, okay, well, what if I'm making new rock here? And this new rock pushes the continents apart. And that would explain why the ocean looks like this and not just like a bathtub. What was brilliant about this is that nobody still had any idea there was a mantle under there convecting. Nobody had any idea. Those mathematical models with Peccaris were ideas, but not, I mean, nobody knew it was inside the Earth. So it's like, okay, well, what if the Earth is like a bowl of soup? But this thing of Harry Hess is fascinating. So I will put up the paper for those who are very keen. You don't have to read it. I'm not going to put an exam or anything, but it's interesting to read. And then there was a group, Morley, Vine, and Matthews, who managed to hook up what this guy said, Hess, with the magnetic reversal idea and say, well, if this is all true, what we should see on the seafloor is magnetic reversals. Okay, and that is what was found. Okay, now what was cool about Morley, Vine, and Matthews is they didn't actually have observations. That was a prediction. So they said, let's take Harry Hess's idea and make a prediction about magnetic reversals. That if all of this theory about stuff moving apart is true, should appear as evidence, and it did later. Okay, so this is the fun part. If we look at that time, a century ago, we didn't have seafloor observations of magnetism, but we could look at a volcano, and we had these evidences of magnetic reversals. Okay, so one thing is that the pole seems to move around because the continent does this, but that doesn't explain how it goes flip. So the magnetic field must also be doing something. And so they said it seems to be flipping. We have evidence in the volcanoes. And then the proposal of Morley, Van, and Matthews was then, if that's true, and every now and then, every few million years, the pole goes boom, we need to really see this on the ocean floor to be convinced that we're creating new rock all this time. And that's what happened in the 1950s. They did magnetic surveys on the ocean floor, and they found these little stripes. Okay, so there's not really anybody around now who doesn't believe that plate tectonics is the best explanation for all of these things. But as I said, the tricky parts are in the details and the little mathematical calculations you'll have to make to understand consequences of this, right? Continental border areas are very complex. One thing we still don't know, for example, when we have a subduction zone, we know that it's moving down, okay, so we can make that little cartoon. But for a long time, it was thought, well, we just have stick slip, right? So we go big earthquake, big earthquake, big earthquake. Okay, we understand that. But the subduction zone structure is more complicated. Do you guys study a little bit of this in seismology? Because even with this plate tectonic theory, the details are quite weird. So it's been very few years since they discovered what are called slow slip events. And I don't know, has everybody here taken seismology? Okay, Juan Pablo?
No, I did take the course, but we didn't emphasize in seismic activity, honestly. But in mechanical continuity, yes.
Okay, because yeah, you do some fault mechanics in Mecánica de Continuo, see? This is, okay. Because one thing that's very interesting, as I think I mentioned before, that studying earthquakes is a geodynamics study. Seismic waves are observations, but for me, the study of earthquakes is really a geodynamics problem. And I say that for a few reasons. One of them is the mechanisms of how parts of the fault slip and other parts don't is really a matter of understanding the forces and the material properties, which is geodynamics. And weird things like how a subduction zone can move only here, move constantly in this part, and then have another part where it's doing slow slips. There's quite a weird dynamic that has to do with the temperature dependent properties and the pressures there that is still, we don't really understand very well, okay? Earthquake prediction, of course, is still non-existent, really. We can maybe use stress fields to predict where is more likely, but until you really understand the dynamic, it's very hard to make any seismic predictions, for example, okay? So this is, I mean, you probably until a graduate course, but it's interesting to think about that, you know, as much as we understand about tectonics, the details, just like Einstein's gravitational equations, we're still fighting about that stuff. Okay, so it's interesting for you guys. Okay. ¿Alguien necesita traducción a español de alguna parte? ¿Entendieron la parte de cambios de dirección magnética y eso cómo se empata con las observaciones de fondo del mar? ¿Todo bien? Okay. Porque ahora la teoría de placas tectónicas es muy completa a nivel global. Ya entendemos muy bien el tema de convección. Tenemos muchas predicciones que llegaron a pasar. Entonces, los detalles ahora son interesantes, ¿sí? De por qué, por ejemplo, en el mismo Colombia, oh, something happened with my, bueno, desaparecí, es que me pareció algo raro. Algo, por ejemplo, en Colombia que de pronto ustedes han observado es esa diferencia en los ángulos del mismo slab que debajo de Colombia y se pueden ver en los sismos. Entonces, la pregunta es, ¿qué provoca eso? ¿Por qué pasa? Y pues se trata de hacer modelos de cómo puede pasar eso y por qué, y cómo es el mecanismo y qué predicciones podemos hacer de eso. El misterio de la raíz cortical faltante en Santa Marta, que que ya ha sido bien estudiada en términos de observaciones, porque todavía nadie sabe exactamente por qué y hay diferentes propuestas. Entonces, ese tipo de detalles, sobre todo cuando hay misterios que parecen no ser consistentes con las predicciones de la tectónica, es lo que hace más interesante. ¿Listo? Okay. I have in this presentation a little bit of a review of the very basic first year level stuff, like Wilson cycles and reminders of like all that went into plate tectonics. Okay. And I talk a little bit about each border type, which I won't bore you. You guys have seen this already. But what's interesting is we're going to look in detail in the next few weeks about how this really works in details. Like, okay, so I'm pushing these plates apart. How do I generate enough force to do that? Why do I subduct at a certain angle? Why does the lithosphere get thicker here? Right? What is actually driving it? There's still a little bit of argument in the scientific community about which forces on the plates really dominate, right? So we know that this is inclined a little bit, and so that there's some weight pushing this way. So maybe we can think of this as like something sliding down a hill, right? So I put a big slab slate shaped like this on a surface and it goes, right? But if the mantle is doing this, does that mean it's actually not slipping? It's just carrying it along? In which case, what's the force pushing on the plate? Do I have this pushing this way, or do I have friction resisting it? Okay, so we can go into the details of like, if I want to do a force diagram on a plate, what should I do? Okay. The continent idea, remember we have this concept of isostasy. How much do you guys remember about isostasy? Or when was the last time you talked about isostasy? Ooh, years ago. Don't tell me how ciencias. You talk about it in geology, yes? Structural geology? Anywhere else? Geophysics? Good. Okay, so you've seen it a couple of times. Isostasy is fun because the math is simple. It's still easy to become confused. I'll give you some isostasy problems in this course because they're like little puzzles. This is really, it can, if we go back to the bump on the bottom of the ocean floor, I think it was Sergio who proposed that maybe the water would be flat. There's some truth in that as a possible consequence, because if I do a gravity survey over the Himalayas, remember, instead of just having this big bump of mass that attracts the plumb bob, they found it attracted it very little. And the question was, why doesn't this big massive mountain attract my gravimeter plumb bob? And remember, the reason is this root. Okay, so it is a bit like a tooth. It's just that unlike our jaws, it's being carried around on top of something, so I don't have to rip out my teeth to move a continent. So there is a root, and what's interesting about that root is that it cancels out a little bit the extra mass that I expect to see at the surface if I just took a continent and went blah, like an ice cream ball. Okay, so I have very less dense continent, and it sinks in, and so all of the mass that's here is almost the same really as just the mass of this piece of lithosphere. Okay. So that's really what isostasy is about buoyancy. When we talked about why Hawaii doesn't sink in like a floating thing, like a floating tooth and go under because it's heavy, we also have these elastic stresses holding up continents, so it's a little more complicated. There's actually a whole book on this. It's called Isostasy and Flexure of the Lithosphere, for people who love the lithosphere. And I'm not saying that as a joke. There's people who only study this topic. But because isostasy works on the idea that things are just freely floating, the reality is a bit different when we put a flexing beam underneath it, or a flexing plate underneath the light thing that's floating. because it does a different thing. And this is can explain why Hawaii doesn't just go into the mantle. Okay, so we'll talk a little bit about how the plates bend and why sometimes like you would expect if isostasy were perfect to have no gravity anomalies. This clearly does not happen. We can look at the gravity anomalies around island chains and convince yourself that this is there's elastic support for these continents. And then so the story gets more interesting than just a floating ball of ice, which maybe is how isostasy is taught in like first year, right? Okay, everybody. That's my very, very brief overview of everything you needed to know about plate tectonics, but forgot in your old courses. And next week, we're going to talk about Euler poles and how to move stuff around and triple junctions. And it's very geometrical. We won't do much physics yet. We'll get into the physics when we start treating plates as real plates and not just imaginary geometrical things. Okay. Enjoy your weekend. Don't think too much about problems like turupes, but do think about maybe explore a little bit about types of problems that might interest you for a project. And then next week, I'll give you ideas for people who are not sure what they want to do. Okay. Have fun. Please relax this weekend. You don't have any tests yet. It's time to sleep a little bit, and we'll see you next week. Take care, everybody. Thanks, guys. We'll see you soon. One day you'll put on your camera so I can see you. Oh, yeah. See some of you in like 12 minutes. Okay, bye, Christian, and see you soon.